aromatic hydrocarbons, an overview about that. Aromatic hydrocarbons, when we say these are benzene, toluene, xylene, etc., these are just examples. Within xylene, we can have orthoxylene, metaxylene, paraxylene, depending on whether we have the other methyl group at ortho, meta, or para. So if there are two methyl groups, we call it xylene. These are the examples of aromatic hydrocarbons because aromatic ring is there and there are only carbon and hydrogen hydrocarbons. Aromatic compounds containing benzene ring are known as benzenoids, and those not containing a benzene ring are known as non-benzenoids. So remember, aromatic compounds can be with benzene ring or without benzene ring. So if we go through this classification here, different types of organic compounds here shown. Aromatic compounds are here, and within aromatic compounds we have three types. Benzenoids means these will have benzene ring. Non-benzenoid means no benzene ring, but still they will be aromatic. And heterocyclic aromatic compounds means there will be some other element also apart from carbon in the ring. So if, for example, here we have nitrogen, all other are carbons here, but this is nitrogen, so heterocyclic aromatic compound. The structure of benzene is depicted like this, and remember, it is not actually like this. This is just used to explain the characteristics of benzene. So this is one of the Kekule's structure. Kekule actually first described this type of a structure. So that's why it is known as Kekule structure. He actually gave two structures, okay, these Kekule's structure. So possibilities are that we can have double bonds here and rest single bond, or we can have double bonds here, alternate double bonds, and the other ones will be single bond. If we try to understand it, how these bonds are formed, on each carbon we have one p orbital in y-axis. So all the p orbitals of carbon, okay, all carbons basically, which are in y-axis, they are parallel to each other. Because they are parallel to each other, there can be parallel overlapping. So here if you see parallel overlapping between these two p orbitals can happen. So we can have this pi bond. Parallel overlapping between these two can happen. We will have this pi bond. Parallel overlapping between these two p orbitals can happen. We can have the third pi bond. Now because this is symmetric molecule, the overlapping can be in these ones also. Okay. Instead of the one I have shown, overlapping can be here also. So in that case, the double bond will obviously be here, here, and here. It means this is just for depiction. Double bond will actually be present at all places and single bond will be present at all places. So no bond will be actually single bond or double bond. These bonds will actually be hybrid bonds, somewhere between single bond and double bond. All will be hybrid bonds, and that's why you might have seen that benzene ring is shown like this, a circle inside, just to depict that all the bonds are same, somewhere between single bond and double bond. So benzene is actually hybrid of various resonating structures. These two are known as Kekule's structure. In reality, what happens, because we have all similar bonds, all bonds are similar, what happens that all the lobes which are at the top, all the lobes of p orbital, py, okay, in y-axis, these are parallel, these combine, these merge, and they form a disc shape at the top, and all the lobes of p orbital, py, on the lower side, bottom side, they combine to form another disk at the bottom side. In the middle, obviously, the electron density is least, so there is hole here. Here also there will be hole, but it looks like that we have two disks, one at the top, another one at the bottom. This is actual shape. This has been found through spectroscopy. Now aromaticity, you will certainly get a question, okay, most probably 90% possibility you will get one question on aromaticity, and it is very important topic for IIT NEET as well. So this is Huckel rule we apply to find whether a compound is aromatic or not. 3 points you need to remember, very simple 3 points, okay. First is planarity, means the ring, I am talking about this ring, for example, simplest form, benzene ring. This must be in a plane, okay. So if I draw this ring like this, okay, like this, so it can't be that we have this here, and then this one in some other plane. No, that is not possible. So say these 5 carbons are in one plane, in the plane of a screen, and this carbon is at the top, then it can never be aromatic, okay. It can never be aromatic. So the molecule must be planar. When we say the molecule must be planar, means the ring must be planar. Complete delocalization of pi electrons in the ring should be there, means no carbon can claim that these electrons are mine. I'm showing just the previous diagram here. If you see this one, electrons are merged here together. No carbon can say that these electrons are localized to me, means these electrons are perfectly delocalized. They do not belong to any particular carbon out of the 6 here. So all the electrons must be completely delocalized. Pi electrons, all the pi electrons must be delocalized. Second point. Third point, presence of 4n plus 2 pi electrons in the ring, means if we are talking about these pi electrons, how many should be there? 4n plus 2 should be there. N can be 0, 1, 2, 3, means n can be any whole number. Starting from 0, it can be any whole number, although in books it is written as integer, but integer can be negative as well. So it is better to say whole number. So we can apply it for benzene, for example. We have seen that in benzene, the molecule is planar, all the carbons are in one plane, and all electrons are delocalized. Now we need to check whether it has 4n plus 2 pi electrons. So if we keep the value of n as 0, so it will be 4 into 0 plus 2, that is 0 plus 2, 2 electrons. If we take n equals to 1, so it will be 4 times 1 plus 2, 4 plus 2, 6. And if you see in benzene ring, we do have 6 pi electrons, 2 here, 2 here, 2 here, total 6. So it means it fulfills all the 3 conditions for aromaticity. It is aromatic compound. Okay. Earlier, when they were named, the aromatic keyword basically comes from aroma. So initially, most of these compounds were found to have some aroma, some good smell. So that's why these compounds were named as aromatic. But later on, many compounds showed similar property, but they didn't have good aroma or any aroma. So that's why the definition was modified, and these 3 rules were given by Huckel. So that's why these are known as Huckel rule.